Did you know that a single teaspoon of a substance called dioxin could, in theory, kill 1 million people? Did you know that a single teaspoon of a substance called dioxin could, in theory, kill 1 million people? This startling fact highlights a profound truth about the world of chemistry. It is a field of immense power, capable of creating wonders that define modern civilization. Yet this same power, when mishandled or misunderstood, holds the potential for devastation on a scale that's almost difficult to comprehend. The elements on the periodic table are like a set of cosmic building blocks. Chemists are the architects. They can build bridges to a better future, but can also, sometimes inadvertently, lay foundations for disaster. This duality, creation and destruction, makes chemistry's story utterly compelling and vital. Before we explore the shadows, it is essential to first acknowledge the light. The clean water that flows from your tap is a product of chemical purification processes, such as chlorination, which helped eradicate waterborne diseases. The food you eat for breakfast is kept fresh by chemical preservatives. Its nutritional value is enhanced by fertilizers. Your morning routine is a testament to the power of applied chemistry. Car, bus, train. Lightweight alloys that make vehicles fuel efficient, durable plastics that form interiors, synthetic rubber of tires, the fuel that powers engines. The smartphone in your pocket would be impossible without chemistry. Its vibrant screen relies on liquid crystals. Its processing power comes from silicon wafers. Its long-lasting battery is a miniature chemical power plant. Antibiotics fight infections. Synthetic insulin manages diabetes. Analgesics alleviate pain. Vaccines are developed using complex biochemical principles. In the early morning hours of December 3, 1984, a catastrophic event unfolded in Bhopal, India, that would become the world's deadliest industrial disaster. A pesticide plant, owned by Union Carbide India Limited, released a massive cloud of methyl isocyanate gas, a highly toxic chemical used in the production of pesticides. The leak began when water entered a storage tank containing over 40 tons of the volatile substance. This initiated a runaway exothermic reaction, causing a rapid increase in temperature and pressure inside the tank. The safety systems, which should have contained such an event, were malfunctioning or switched off, were woefully inadequate to handle the scale of the reaction. A dense, toxic cloud drifted over the sleeping city, blanketing the densely populated shantytowns surrounding the plant. Methyl isocyanate is a severe irritant. Upon inhalation, it causes burning in the lungs and eyes, leading to suffocation, leading to blindness. Thousands of people died in their sleep or as they fled in panic, their lungs ravaged by the chemical. The long-term impact on survivors and the environment has been profound and continues to this day, decades later. The solution: mandatory implementation and independent auditing of robust, multi-layered safety systems, functioning warning systems, regular maintenance, adequate staff training, a comprehensive emergency response plan developed with local communities. In the late 1970s, a quiet, middle-class neighborhood in Niagara Falls, New York, became the unwilling poster child for a new kind of environmental threat: toxic waste. The neighborhood, known as Love Canal, was built on land that had previously been used as a chemical landfill by the Hooker Chemical Company. Between 1942 and 1953, the company buried nearly 22,000 tons of industrial chemical waste in an abandoned canal. The waste cocktail included a host of notoriously toxic and carcinogenic substances, such as benzene, dioxin, various pesticides. After filling the canal, the company covered it with a layer of clay and sold the land to the local school board for $1, with a deed that mentioned the chemical waste but downplayed the risks. Unusually heavy rainfall caused the groundwater level to rise, bringing the buried chemicals to the surface. Oily, foul-smelling black sludge began to ooze into basements and seep into yards. Children playing in fields developed chemical burns on their skin. Trees and garden plants turned black and died. The fight for answers was led by the residents themselves, most notably by a determined homemaker named Lois Gibbs, who organized her neighbors to demand action. Scientific studies by the Environmental Protection Agency confirmed toxins in the air, soil, water. In 1978, President Jimmy Carter declared a federal emergency, leading to evacuations. The one-line solution: enforce cradle-to-grave responsibility for hazardous waste, securely contain, track, safely dispose of it in designated, isolated facilities. The disaster led to the EPA's Superfund program in 1980, a law designed to fund the cleanup of abandoned toxic waste sites across the United States. On the coast of the Shiranui Sea in Japan, the city of Minamata was home to a fishing community whose lives were deeply intertwined with the bounty of the ocean. In the 1950s, a mysterious and terrifying illness began to appear among the local population. It started with strange symptoms: numbness in the limbs, difficulty walking, slurred speech, uncontrollable tremors. In severe cases, it led to insanity, paralysis, coma, and death. The affliction became known as Minamata disease. Cats in the area convulsed and fell into the sea, dancing cat fever. The source was traced to the Chiso Corporation, which discharged wastewater containing methylmercury into Minamata Bay. Mercury had been used as a catalyst in the production of acetaldehyde. This highly toxic organic mercury accumulated in the marine ecosystem, from plankton to small fish to larger fish, and to the people who ate them. The poisoning crossed the placental barrier, harming developing fetuses. Babies were born with severe congenital defects, including profound intellectual disabilities and cerebral palsy, even when mothers had few symptoms. The corporation initially denied responsibility, and the government response was slow. Years of struggle were required for recognition and accountability. One-line solution: mandate the complete prohibition of discharging untreated industrial waste, especially heavy metals like mercury, into any body of water, and rigorously monitor industrial effluent. Minamata remains a powerful reminder of the intergenerational damage when industrial profits are prioritized over human health and environmental stewardship. In the 1970s, scientists began to notice something alarming high up in the Earth's stratosphere. The ozone layer, a vital shield of gas, was absorbing UVB radiation, but it was thinning dramatically over Antarctica. It became so pronounced it was dubbed the ozone hole. A depleted ozone layer means more UVB reaching Earth's surface, leading to increased skin cancer and cataracts in humans, damage to crops, harm to marine ecosystems. The culprits: chlorofluorocarbons, CFCs. CFCs contain chlorine, fluorine, carbon. They were once hailed as miracle chemicals: non-toxic, non-flammable, incredibly stable, perfect for industry. Their stability was the problem. They didn't break down in the lower atmosphere and drifted into the stratosphere, where UV radiation broke them apart, releasing chlorine atoms that catalytically destroyed ozone. Mario Molina and Sherwood Rowland proposed this chemistry in 1974. Industry was skeptical, until dramatic Antarctic satellite images forced action. The solution? Phase out ozone-depleting substances via international agreement. The Montreal Protocol, 1987, ratified by every country, mandated a gradual ban on CFCs. Industries innovated safer alternatives. The ozone layer has begun to slowly heal, proving that united behind science, the world can solve daunting environmental challenges. On April 20, 2010, the Gulf of Mexico became the site of the largest marine oil spill in history. The disaster began with a surge of methane gas from a deep-sea well that blasted up a drill pipe to the Deepwater Horizon oil rig. The gas ignited, causing a massive explosion that killed 11 workers and engulfed the rig in flames. 2 days later, the platform sank. The damaged wellhead began gushing crude oil into the Gulf. For 87 agonizing days, oil flowed unchecked. An estimated 210 million gallons entered the marine environment. Crude oil contains thousands of hydrocarbon compounds. Many are toxic to living organisms. Vast slicks coated birds and marine mammals, robbing them of the ability to regulate body temperature and stay afloat. Massive underwater plumes poisoned fish, plankton, and organisms at the base of the marine food web. Millions of gallons of chemical dispersants broke oil into smaller droplets, also introducing new chemicals with long-term effects still not fully understood. The Gulf Coast economy was devastated. Fisheries, tourism, beaches coated in tar balls and public confidence shattered. Coastal marshes eroded. Studies documented harm to dolphins, sea turtles and deep-sea coral communities, with full impacts unfolding over decades. Failures of technology, management, and regulation. One-line solution: mandate redundant, fail-safe safety technologies in offshore drilling, rigorously tested under independent oversight. After examining these sobering accounts of chemical disasters, it is natural to feel a sense of unease about the role of chemistry in our world. However, the same ingenuity that created these problems is also our greatest hope. Green chemistry, also called sustainable chemistry, is a guiding philosophy. It is the design of chemical products and processes that reduce or eliminate the use and generation of hazardous substances, built upon 12 core principles. Design safer chemicals with minimal toxicity. Use renewable feedstocks, plants, biomass, instead of depleting fossil fuels. Design energy-efficient processes. Use catalysts. Create products that biodegrade harmlessly. We are already seeing impact. New plastics from cornstarch and vegetable oil that can be composted instead of lingering in landfills. New, less toxic solvents. Greener drug synthesis. These practical, economically viable solutions show environmental responsibility and economic success are not mutually exclusive. Transitioning to green chemistry is a defining challenge of this century, requiring chemists, industries, governments, and consumers to act together. The stories of Bhopal, Love Canal, Minamata, the Ozone Hole, and the Deepwater horizon are not just historical footnotes. They are living lessons, etched in the soil, the water, and the health of generations. Chemical progress without caution is a gamble. Too often, short-term profit eclipsed long-term safety and community well-being. Each of us can foster a culture of chemical safety by staying curious and informed, understanding products we use, and staying aware of local environmental issues. Share knowledge, support science education, back policies and leaders who champion strong environmental regulations and green chemistry investment. We can react to disasters or proactively build a world where they are prevented. By supporting transparent, sustainable companies, advocating robust safety standards, and championing green chemistry, we steer this powerful science to serve all life on Earth. The elements are waiting. It is up to us to combine them with wisdom and foresight.